Welcome! Today, we're going to crack the universe's secret code. We're talking about the fundamental building blocks of, well, absolutely everything. Your desk, the air you're breathing, even you. So, let's dive right in. I want you to just think about this for a second. What if all the incredible, complex stuff we see around us, what if it all boils down to just a handful of simple ingredients, just combined in different ways? That's exactly the journey we're going on today.
So let's meet those ingredients. In the world of chemistry, we call them elements. These are the purest substances you can get. They can't be broken down any further, and each one has its own totally unique personality.
Now, on a really basic level, we can sort of group these elements into two main flavors, just based on things we can see and touch. First, you've got your metals. You know them. They're typically shiny, which we call luster, and they're solid. And on the other hand, you have the non-metals. They tend to be dull, and they can be gases or even brittle solids.
But to really get why they're all so different, we've got to go deeper. A lot deeper. We're going to zoom way in, past the element itself, and start peeling back the layers to see what's really going on inside.
And right at the heart of every single element is the atom. Now this is the key. An atom is the smallest possible piece you can have that still is that element. You see, if you break it down anymore, it's not gold anymore. It's not oxygen anymore. It becomes something else entirely.
And here's the really wild part. Every atom in the entire universe is made from just 3 tiny particles. Right in the center, the nucleus, you've got your positively charged protons and your neutral neutrons. And then, zipping all around the outside are the negatively charged electrons. That's it.
So let's look at the numbers here. The charges are pretty simple, right? +1 for a proton, 0 for a neutron, -1 for an electron. But look at the mass. This is where it gets crazy. A proton or a neutron is almost 2,000 times heavier than a teeny tiny electron. That means pretty much all the weight, all the substance of an atom is crammed into that incredibly small nucleus.
And here it is. If you remember one thing from this explainer, make it this. An element's identity, its very essence, comes down to just one thing: how many protons it has. We call that its atomic number. If an atom has 6 protons, it is carbon, period. If it has 7, it's nitrogen. It's the unique fingerprint for every single element. Okay, so if the protons give an element its identity, what gives it its personality? You know, how it acts, what it reacts with. Well, for that, we have to look at the electrons. Which kind of brings up a huge question, doesn't it? If a lump of sodium and a cloud of chlorine gas are both made of the exact same 3 particles, why is one a soft, shiny metal you can cut with a butter knife, and the other is a deadly green gas? The answer is all about location, location, location. It's not just that these elements have electrons, it's where those electrons are. The way they're arranged in these shells around the nucleus, well, that dictates everything. You can think of it like each electron has its own unique address. Now, I know this diagram looks a little complicated at first, but it's really just a map. It's a tool for finding an electron's address. You literally just start at the top and follow those yellow arrows, filling up each level as you go. It's like a visual roadmap for any element's electrons.
So let's take sodium, for example. It has 11 electrons. If we follow that path, we get this address you see right here. Now, the most important part is that last electron. See it? The one all by itself in the outermost shell. We call that the valence electron, and it defines sodium's entire personality. It's lonely out there, which makes it super eager to react with other elements.
All right, so protons give an atom its identity, and the electron's address gives it its personality. But how in the world are we supposed to keep all of this straight? Well, luckily for us, there's an ultimate cheat sheet where all of this information is organized brilliantly. It's the periodic table. And please, don't think of this as some scary chart you have to memorize from school. It's not. It's actually a masterpiece of organization. It's a map where every single element is placed perfectly according to its atomic number and, you guessed it, its electron address. And because it's organized like this, something amazing happens. Elements in the same vertical column form families that have really similar personalities. Take group 1, the alkali metals. They're all ridiculously reactive because they all have just one of those lonely valence electrons they can't wait to get rid of. Then you've got group 18, the noble gases. They're the total opposite. Their outer shells are completely full, so they're stable, they're happy, and they just don't react with anything.
So far, this has all been kind of abstract, right? We're talking about things we can't see.
But now, we're going to connect all this theory to something we can actually see with our own eyes. We're going to make the invisible world of the atom visible.
So why does all this electron address stuff matter in the real world? Here's why. It's because the movement of electrons is literally the source of light. When an electron jumps between those energy levels, or shells, that we were talking about, it either absorbs or releases energy in the form of light.
This shows you exactly how it works. On the left, an electron absorbs some energy, let's say from heat, and it gets excited, so it jumps up to a higher energy level. But it can't stay up there forever, so it eventually falls back down. And when it does, bam, it releases that extra energy as a particle of light. The specific distance it falls determines the exact color of that light, which creates a unique color fingerprint for each element, just like you see on the right.
And this isn't just theory. We can see this happen right in front of us in something called a flame test. When we put a chemical into a flame, the heat gives the electrons the energy they need to make that jump. And as they fall back down, they release that energy as these beautiful, specific colors.
And that is the key takeaway here. Each element produces a unique and characteristic color. That color is a direct, visible sign of its unique electron structure. It's the atom's personality literally shining through for us to see. Which really leaves us with one final thought. If the dance of electrons inside a tiny atom can paint the colors of a flame, just think about what else they're responsible for. The glow of a neon sign, the brilliant colors of fireworks, even the light from stars billions of miles away. So what else in our universe are they coloring?